Hello everyone, this is Yogita R. Today I am going to discuss about conversion of NFA to a DFA, which comes under the subject Automata Theory and Compiler Design. The topics discussed in this video are: what is an NFA, what is a DFA, steps to convert NFA to DFA, an example of converting NFA to DFA, and uses of converting NFA to DFA. Now let us see what is a DFA. Deterministic finite automata or DFA are finite state machines that accept or reject string of characters by parsing them through a sequence that is uniquely determined by each string. The term deterministic refers to the fact that each string and thus each state sequence is unique. Here is an example of a DFA. What is a NFA? NFA stands for non-deterministic finite automata. It is easy to construct an NFA than DFA for a given regular language. The finite automata are called NFA when there exist many paths for specific input from the current state to the next state. Here is an example of an NFA. Conversion of NFA to DFA. Here are the steps involved in converting NFA to DFA. Step 1. Convert the given NFA to its equivalent transition table. To convert the NFA to its equivalent transition table, we need to list all the states, input symbols, and the transition rules. The transition rules are represented in the form of a matrix where the rows represent the current state, the columns represent the input symbol, and the cells represent the next state. Step 2. Create the DFA's start state. The DFA's start state is the set of all possible starting states in the NFA. Step 3. Create the DFA's transition table. The DFA's transition table is similar to the NFA's transition table, but instead of individual states, the rows and columns represent set of states. For each input symbol, the corresponding cell in the transition table contains the epsilon closure of the set of states obtained by following the transition rules in the NFA's transition table. Step 4. Create the DFA's final states. The DFA's final states are the set of states that contain at least one final state from the NFA. Now let us see an example of how to convert an NFA to a DFA. We have to construct the transition diagram first. From the figure we can see that Q0 on giving 0 it goes to Q0, and Q0 on giving 1 it goes to Q1 Q2, and Q1 on giving 0 it goes to Q1 and Q2. Q1 on giving 1 it goes to Q2. Q2 on giving 0 it goes to Q0 and Q1. Q2 on giving 1 it goes to Q1. Here Q0 is the starting state and Q2 is the final state. Steps. In the first step, we have to find the transition of Q0 with respect to 0 and Q0 with respect to 1. Transition of Q0 with respect to 0 is Q0, and transition of Q0 with respect to 1 is Q1, Q2, which is a new state. And transition of Q1, 0 is Q1, Q2, and transition of Q1, 1 is Q2. Transition of Q2, 0 is Q0, Q1, and transition of Q2, 1 is Q1. And we have to find the transition of the new states. Transition of Q1, Q2 with respect to 0 is transition of Q1, 0 union transition of Q2, 0. Transition of Q1, 0 is Q1, Q2, and transition of Q2, 0 is Q0, Q1. And when we apply union operation, it becomes Q0, Q1, Q2, which is another new state. Transition of Q1, Q2 with respect to 1 is transition of Q1 with respect to 1 union transition of Q2, 1. Transition of Q1, 1 is Q2, and transition of Q2, 1 is Q1. When we apply union operation, it becomes Q1, Q2. And transition of Q0, Q1, Q2 with respect to 0 is transition of Q0, 0 union transition of Q1, 0 union transition of Q2, 0. Transition of Q0, 0 is Q0, transition of Q1, 0 is Q1, Q2, and transition of Q2, 0 is Q0, Q1. On applying union operation, it becomes Q0, Q1 and Q2. Transition of Q0, Q1, Q2 with respect to 1 is transition of Q0, 1 union transition of Q1, 1 union transition of Q2, 1. Transition of Q0, 1 is Q1, Q2. Transition of Q1, 1 is Q2 and transition of Q2, 1 is Q1. On applying union operation, it becomes Q1, Q2. Transition of Q0, Q1 with respect to 0 is transition of Q0, 0 union transition of Q1, 0. Transition of Q0, 0 is Q0 and transition of Q1, 0 is Q1, Q2. On applying union operation, it becomes Q0, Q1 and Q2. And transition of Q0, Q1 with respect to 1 is transition of Q0, 1 union transition of Q1, 1. Transition of Q0, 1 is Q1, Q2 and transition of Q1, 1 is Q2, which becomes Q1, Q2. And we have to draw the transition table according to the steps and draw the DFA according to the transition table. Here we can see that Q0 is the starting state and Q2, Q1, Q2 and Q0, Q1, Q2 are the final states. The final states are represented in double circles. Q0 on going to 0, it goes to Q0. Q0 on giving 1, it goes to Q1, Q2 as shown in the diagram. Q1 on giving 0, it goes to Q1, Q2. Q1 on giving 1, it goes to Q2. Q2 on giving 0, it goes to Q0, Q1. Q2 on giving 1, it goes to Q1. Q0, Q1 on giving 0, it goes to Q0, Q1, Q2. And Q0, Q1 on giving 1, it goes to Q1, Q2. And Q1, Q2 on giving 0, it goes to Q0, Q1, Q2. And Q1, Q2 on giving 1, it goes to Q1, Q2. Q0, Q1, Q2 on giving 0, it goes to Q0, Q1, Q2, which means nothing but the self loop. And Q0, Q1, Q2 go with 1, it goes to Q1, Q2. And here you can see Q2, Q1, Q2 and Q0, Q1, Q2 are the final states. Now let us see the uses of converting NFA to DFA. Deterministic behavior. DFAs have deterministic behavior, meaning that for a given state and input symbol, there is only one possible transition. This makes it easier to understand and analyze the behavior of the automation. Efficient implementation. DFAs are often more efficient to implement than NFAs. Deterministic machines can be implemented using simple lookup tables or switch case statements, making them computationally less expensive compared to the more complex execution of non-deterministic choices in NFAs. Memory efficiency. DFAs typically require less memory than equivalent NFAs. The state transition table of a DFA can be represented more compactly, as there is a direct mapping between states and the transitions. Deterministic language recognition. Some applications, especially in formal language theory and compiler design, require deterministic language recognition. DFAs are more suitable for such applications as they guarantee a unique path for each input. Optimized parsing. In computer construction and parsing theory, DFAs are commonly used in lexical analysis, tokenization, to efficiently recognize patterns in the input. Deterministic lexers simplify the parsing process and are more straightforward to implement. Tool support. Many formal verification and analysis tools are designed to work with DFAs due to their deterministic nature. Converting an NFA to a DFA allows leveraging these tools for more efficient analysis and verification of the corresponding language. Compatibility with existing systems. Some systems, especially those designed for industrial applications or legacy systems, may only support deterministic machines. Converting an NFA to a DFA allows seamless integration into such systems. Thank you.